Hello students, good day. I hope all of you are well. In the previous lecture, we discussed several multi-threading models as well as had some introduction about synchronization. In the today's lecture, we will try to uh, broaden our understanding about synchronization and various classical problems that are involved with it. In synchronization, as we discussed in the previous lecture, that when we have multiple threads working together in an environment that supports uh, multi-programming, so they have to cooperate with each other because we may have some shared data and multiple threads they are trying to assess that shared data in a concurrent way. So we require some cooperation among multiple threads so that the data remain consistent. So all of this synchronization stuff involves with the consistency of data and making sure that in the presence of multiple threads, the data should remain intact or it should be modified in a legitimate way. When we are discussing synchronization, we have to ensure about dependencies and the precedence of multiple processes, as well as in the presence of multiple threads, we have to see which of them executed prior to the other. The race condition is a very important and a basic problem that is associated with synchronization. In race conditions, we have multiple processes or threads, and they want uh, to manipulate a shared data uh, in a concurrent way. So if they are assessing it and if they are modifying the shared data in a concurrent fashion, then there are multiple things that can be raised in this condition. And because the data is shared, there are chances of inconsistencies that can appear if the order of the execution of thread if they change. So the final value of the shared data, it may depend on the order of the execution of multiple threads. So which thread finishes at the end, it will impact the outcome of the final shared data. So usually to prevent this race condition, we have synchronization mechanisms that ensure that these processes they are synchronized and they are working in accordance with each other. As its name suggests, race condition means that multiple threads they are in a race with each other, and dependent on their position in that race, the final outcome of the program or the result of a task is dependent on their final position in that particular race. So over here we have an example. So as you can see that on top we have an implementation of increment operation. So you can see that counter variable is stored in a register, then the value of that register is incremented, and then the variable counter is again replaced with the modified value of the register 1. On the other hand, if we have counter minus minus, we may have this decrement operation implemented as such. So now just consider that both of these operations, they are listed in a sequence, and there are multiple threads which are trying to execute them in parallel in a concurrent fashion. So for instance, if such is the case, this can be the order of execution of these statements. So if the value of this counter variable is set to 5 initially, we have an increment operation and then we have a decrement operation, and that should actually result in 5. So incrementing it will make it 6 and then decrementing it will make it 5 again. However, as the order of these instructions can be manipulated, so the final result will be different in this case. So you can see that for instance, the value of this counter is stored in the register, then the register is incremented, and the very same value, the old value of the counter, is now saved in register 2, and which is decremented. Now you can see that if it is 5, it will become 6, but this modification is not yet reflected in this counter variable. So the old value of this counter variable will be stored in the new register, and now the value of this register is decremented. Now based on the order of their completion, you will see the difference in their final outcome. So either it will be 6 or either it will be 4, dependent on which of these two instructions execute at the end. So now you can see that instead of having the legitimate result, that is 5, we end up either having 6 or 4, which is definitely not the right outcome. So this is the race condition, and we want to ensure that if we have such a condition where multiple threads are executing on a shared data, then their order should not affect the final output, or no matter what is the order of their completion, we should have a legitimate result. So critical section is a section like this that we have encountered on the previous slide, where we have multiple threads or multiple processes, and they are trying to use the shared data, and they are all competing with each other in execution. So now it is possible that we may have a shared code segment in terms of multiple threads, and the order of execution may impact the final outcome. So we call that particular section as the critical section, which means that the order of execution does matter in this critical section, and we have to, while implementing it, we have to take extra precautions just to ensure that whatever the order is, whatever the scheduling stuff is going within the operating system, your code and its final outcome should not get affected by the order of execution of multiple threads or multiple processes. So we try to ensure multiple ways through which this can be handled. There are semaphores, there are mutex, there are locks, there are monitors. So we will just try to generalize it to make it simple for today. So the problem that we have over here is that once if one particular process is executing in the critical section, no other process should be allowed to enter in this critical section. In this way, we ensure that only one thread or one process may execute this critical section at a particular time. And once it completes its execution and it moves out of this critical section, then some other process or other thread can enter this critical section. So in this way, we can synchronize multiple threads or processes to cooperate with each other. Usually it can be done through shared variables, it can be done through message passing. So there are multiple ways in which it can be dealt with. So over here we have a simplified solution to this problem. So over here, as you can see, that we have a critical section in here at the middle, and we have this entry and we have this exit. So we put some restriction on this entry, ensuring that multiple competing threads should not enter in this critical section at any point in time. So for this particular stuff, we use some flags, some variables, and for instance, if before entering, if we just set a particular flag to true, and while we restrict other processes to only enter this critical section if the thread is false. It is just like if we have a some high confidential room. Sometimes you have seen this in hospitals where they have uh, a red bulb in front of some rooms, particularly in X-ray rooms, and that reflects that you should not enter this section. So just like that, if we have a flag raised and we define that a thread cannot enter in this section if this flag is off or on, and then when you are implementing it, when the other thread enters this critical section, dependent on the implementation detail that you had earlier, you can now put this flag as on and off, and then you ensure that only this particular process is executing at any particular time. A semaphore is an abstract data type that can be used to restrict the access of multiple threads or processes to a shared data or a common resource, so that they do not interfere with each other, or they do not pose an impact on the final outcome of a process. So let me elaborate on this point. So for instance, if you have shared data that is being shared by multiple competing threads, or if you have a resource that is being shared by multiple processes, so and they are competing with each other to get this resource. So in such situations, you may want to have some mechanism to ensure that the final outcome should not get affected by the order of execution of these threads or processes. So semaphores provide us a mechanism, an abstract mechanism, so that we can restrict multiple threads or processes to use or to access a common resource. However, when we are implementing mechanisms to restrict the access of a process or a thread to a resource, it is possible that something may go wrong, and a thread may not come out of a critical section ever. So in such case, the flag will not return to false or true, dependent on your implementation, and all the other competing threads which are waiting in this case, they may have to wait for infinite amount of time. So whenever we have scenario where some process or thread has to wait for other resources, threads, processes to be released or to complete their execution for indefinite amount of time, we term this scenario as starvation. Starvation means that a process is waiting, and it will never be removed from the waiting state because some other thread or some other process is utilizing the resource which made this thread or process suspended for a while. And this suspension is transformed into an infinite blocking, and which will make sure that the execution of this thread will never be scheduled for the processor. And if such is the case, we may term it as starvation, and we will say that the scheduling of this process or thread may never occur. You may have already associated this term with CPU scheduling when we were discussing priority scheduling, or when we had this shortest job first. So you can see that the longer process in shortest job first, or processes with low priority, they may have to starve for an indefinite amount of time. This starvation, if it gets extended to other processes, we may have deadlock in a system. The difference between a deadlock and a starvation is that when we have starvation, there are processes that are blocked. However, at the same time, there are other processes that are still executing in the system. So the system resources are still in use. However, when this thing extends to other processes, and when all of the processes present in a system, they may not be able to execute themselves because the resources that they require for their execution may be occupied by other processes. We have a state of deadlock in the system. Deadlock means that multiple processes, or at least two processes, they are waiting for each other, or waiting for the resources occupied by other processes for an indefinite amount of time. When we have multiple processes in a system and none of them can get execute because their required resources are occupied by other processes, then we have a state of deadlock in the system. There are various characteristics of deadlocks, and there are various variations through which we can handle deadlocks as well. We will discuss this terminology in more depth in the coming lecture. However, today, just having an overview of deadlock and how the system will look like once we have a deadlock in there, so we will discuss it just in a bit today. Over here, we have a visualization of a deadlock. So you can see that in such condition, no process can complete its execution because the resources that are required by this process is occupied by other processes. So we have identified a number of reasons and characteristics why deadlocks occur in any system, and we will discuss them in the next lecture. So after having a basic understanding of deadlocks, starvation, and their impact when we have a synchronization requirement in the whole system, now let's discuss some classical problems of synchronization. Over here, we have several classical problems of synchronization. These classical problems were defined to reflect various scenarios that can present in any computing environment. So these problems are developed so that whenever we have some situation in a computing environment and we require solution to that particular problem, we may refer to some classical scenarios or classical problems to borrow a solution to the recent problem that we are facing. So understanding these problems can lead to a deeper understanding of any concept. In today's lecture, we will discuss three classical problems of synchronization, including producer-consumer problem, reader and writer problem, and dining-philosophers problem. So all three of them have different implications, and their solutions can refer in different computing problems domain. The first problem is producer-consumer problem. Producer is an entity that produces some information or some data, while consumer is another entity that consumes that data or information. There can be several examples in a computing environment referring to this producer-consumer problem. An example can be or print programs where we have a series of characters that are produced by a program, some processor, some word processor, and they are consumed by the printing device or the printing driver in order to print them out onto a piece of paper. Also, our compiler may produce some assembly code that is consumed by the assembler. So producer is some entity that is used to produce something, while the consumer is an entity on the receiving side that receives the information or consumes that information. So when we have some producer and consumer entities in a system, we may have several issues that can be raised in such situation. The first one can be the buffers. Buffers can be referred to as some space that is being filled by the producer and that is being consumed by the consumer. So you can have an analogy of some factory line where the production is in process, and the finished product is being placed onto some warehouse from where it is being consumed by the consumer. So producer is some entity that is producing something, while consumer is another entity that is at the receiving side that consumes that particular information, data, result that is being produced by the producer. So when we have producer as well as consumer and we have a shared common space, then all of these things should be synchronized. The producer and consumer should be synchronized about the shared space so that the producer may not produce something that cannot be consumed or may not fill the whole shared space by its output while it is not being consumed by the consumer. Also, at the consumer side, the consumer may not be slow enough to consume the resources or the information that is being produced by the producer and let the shared space filled by the information produced by the producer. At the same time, it should not be efficient enough in comparison with the producer so that it consumes everything and it tries to consume some information that is not yet being produced. So in this environment, both producer and consumer, they have to wait for each other, or a better way to put it is that they have to be synchronized with each other so that the producer may wait for the consumer to consume at a appropriate pace, while the consumer has to be synchronized with the producer so it consumes the resources or the information at some appropriate pace that is compatible with the producer. There are some variations of this producer-consumer problem. The first one is that the size of the buffer can be either bounded or unbounded. Bounded buffers means that the size of the shared space that is fixed, so both producer and consumer, they have to wait for each other in order to consume or produce the resources. or the information. While in the unbounded buffer variation, the producer may produce as much data as it wants, as the shared space where it is putting all the information is unbounded. It's close to unlimited. So the producer may produce as much data as it wants, while the consumer, it has to wait for the producer to produce something. So the producer may act alone irrespective of the consumer, while the consumer has to be synchronized with the producer or its space. The second problem is readers writers problem. In this problem, a data set is shared among multiple processes that can perform concurrent operations on this data set. We term several processes as readers who just perform operations on the data that do not modify the actual data. So readers are the processes who do not perform any modification on the data set. However, other processes which may be termed as writers are the ones which can perform operations that can modify the dataset. So we have several processes or threads present in the system. Some of them are readers that can only read the data. Some of them are writers which can read as well as can write on the dataset. So the problem that can be associated with this scenario is that because readers may not be able to modify the underlying data set, so we may allow multiple readers to assess the data simultaneously, and it would not affect any concurrency issue, or it would not affect the overall situation or the position of the data. However, if we have a writer process working on the data, then we may not allow any other writer process to work on this shared data at the same time. The reason behind it is that if two writer processes they are working on the same data set, it may lead to some concurrency issue. There are several variations to this problem. However, some underlying principles remain the same in all of these variations. For instance, in some of the variations, it is expected that only one writer may manipulate the dataset at any given time. However, in other variations, we may have multiple writers working on the data set at the same time. However, we may have different versions of the data that may be combined together after a particular set of operations are concluded. However, one thing that is common to all is more than one readers can assess or read the data simultaneously, because they are only reading the data and are not modifying it in any form. So it would not lead to any concurrency issue. There is one more variation that may differ in different scenarios, and that is that if a writer is writing on the data set, then the readers are allowed or to read the data or not allowed to read that data. So there are various variations that may happen in different situations. However, all of these variations, they also again lead to several other sub-problems that are related to this reader-writers problem. Two basic variations where reader processes or the writer processes, they may have to compromise their execution are presented in here. In the first situation, if some reader is reading the file and some writer is there to write onto the file, we do not stop the readers to continue reading the file, which means that if in a scenario we have a reader reading a file and we have a request from the writer, now the writer may have to wait unless the reader completes its job. so that the writer may start modifying the data. However, in the meanwhile, if we have another reader joining in the system and it requests to read the dataset, because there is already one reader working on it, we may allow the second reader to continue with this with its read operation. And the writer again has to wait for both of these processes to complete their execution or to complete their operation on this dataset. However, as you may have observed that this process may not stop other readers to join in the reading process, so the writer may have to starve. So the writer may be kept on waiting just because multiple readers are reading the dataset. So in this scenario, writers may have to starve. In the second scenario or the second variation, if once a writer is ready to write on the dataset, we do not allow any other reader to enter the process to read the data. So once a writer process puts a request to write on the dataset, we do not allow other readers to read the data, and we give precedence to the writer process. Definitely, this can be considered as a solution to the previous variation or situation. However, when we have a precedence of writer over the reader, so it is possible that in a particular situation, if some writer is writing and some reader is waiting for it to complete its job. Meanwhile, we have another writer joining in the system. So now, once the first writer will complete its operation, the second process or the second writer will continue writing onto the data, and the reader may have to starve. So as you have seen that both of these variations, they may lead to starvation for either the writer processes or the reader processes. And again, if we try to solve them, there are other variations which may lead to different scenarios as well. Moving on, the third problem of synchronization is the Dining-Philosophers Problem. In this problem, processes are termed as the philosophers, and we assume that they do not interact with each other. So they are just sitting, and occasionally they start eating and then go back to the idle state. We have in front of them a bowl of rice or noodles, and we have some chopsticks that are present on their table. So each of these philosophers, they have their own bowl of rice or noodles. However, a total of n chopsticks are present on the table. And as you know that uh, in order to start eating, one philosopher may need two chopsticks to eat. So because the number of chopsticks is less than the ones that are required, so we have a shared resource in form of chopstick. So now philosophers, they have their uh, own bowl of rice or uh, noodles. However, they have to share their neighbor's chopstick in order to finish their eating. So now they need both of the chopsticks, which means that their neighbor may not be eating simultaneously as when they are in the eating process. Once they complete their eating, they may release the chopstick back onto the table, and now some other philosopher may be able to pick this up. So you can see that these chopsticks, as they are shared, so they can be represented as semaphores, and two neighbors, they may not be able to eat simultaneously, and still there are several possibilities of deadlock as well. It is possible that a philosopher may pick up the right chopstick, and when it goes to the other one, the left one, it's not there. So the philosopher may keep on waiting for the other chopstick while holding the first one in their hand. And this may lead to a scenario where all of the philosophers, they are holding one chopstick in their hand and they are waiting for the second one, which may lead to a deadlock situation. In computing, if we have a situation similar to Dining-Philosopher problem, we have some variations to deal with the problem of deadlock. The first possibility is that if we have 5 chopsticks available, then we may only allow 4 philosophers to sit on the table simultaneously, which means that at least if every philosopher may pick their chopstick simultaneously, still there must be at least one philosopher who may have 2 chopsticks at any given time, which may lead to completing its operation and then releasing the chopstick once it's done. So in this way, we may not uh, have a situation in the system where all the processes or all the philosophers, they are holding one chopstick and waiting for the other. In the second variation, we may allow the philosophers to pick the chopstick only if both of the chopsticks are available. So we may put this picking up of chopsticks in the critical section. Usually we call it as a transaction in computing. So multiple small processes or operations, they combine together to form a transaction. So either a complete transaction is executed or everything gets rolled back to the beginning of it. In the same manner, in Dining-Philosophers problem, if both of the chopsticks are available, the philosopher may pick them up. If only one is available, it may release the second one as well. For the third variation, we may allow the odd number of philosopher or the philosopher that is sitting on the odd number of chair to pick up his left chopstick first and then moving to the right. At the same time, for the philosopher sitting on the even number, they may pick up their right chopstick first and then left. This will lead to having a contention between 2 philosophers at any given time if they try to pick up their chopstick. Because for the odd philosopher, their left chopstick will be the same chopstick which is the right chopstick of a philosopher sitting on an even seat. So even and odd, 2 neighbors philosophers, they are having contention over the same chopstick, which means that if they are not able to pick up their first chopstick, then it means at least in the whole system at any given time there will be at least one philosopher who is eating. So in systems we have this thing as processes and resources. So usually just by looking at the number of resources that are present at any given time in the system, we have such situations and we have such solutions to them. To summarize today's lecture, we had synchronization, where we discussed deadlocks in journal, and then we discussed the race condition. In the coming lecture, we will discuss deadlocks in a bit more detail. Moving on, we discussed various classical problems of synchronization, including the producer-consumer problem, the reader-writer problem, as well as the dining-philosopher problem. So that is all for today, students. Please take good care of yourself. Thank you.